Hello, welcome back to the channel. So let's do some more questions on calculations of indefinite integral using trigonometric substitution. So again, whenever you see a form of a square plus minus b square expression, it will give you an idea that you have to most probably use trigonometric substitution in order to simplify your indefinite integral or definite integral and then solve for them. And in this case as well, since we have an x square plus 16 term, it resembles the a square plus minus b square term, right? If we take our a to be 4 and b to be 1, a square plus minus b square x square will become 16 plus x square in this case, right? So that is why it gives us an idea that if we try to convert this expression into 1 plus some trigonometric function square expression, we can easily convert the expression by using one of the three trigonometric identities that we know, right? So the same approach that we have been doing in the previous videos. So if you have not watched my previous videos on this approach, on the approach of using trigonometric substitution, I would highly suggest you to first watch my previous videos in order to get the full context of this video. And the videos you can always find on the I button above, or if you click on the description, you can find those videos as well. So let's calculate this integral over here, and since we have x square plus 16 and we know a trigonometric identity that tan square theta plus 1 equals secant square theta, right? That is what we already know about tan square and secant square relationship, right? So if we take our x to be, in this case, if we take our x to be 4 tan theta, x square will become 16 tan square theta, right? So 16 tan square theta plus 16 tan square theta plus 16 in this case will become 16 secant square theta, right? So if we take our x to be 4 tan theta in this case, we can easily simplify this expression as simply calculating the square root of 16 secant square theta, right? And then we can do all those manipulations, conversions of dx and x in every term to solve for the trigonometric substitution by using the same approach which we have been using in the previous videos. So again, in this case, let's take our x to be 4 tan theta. And if we take our x to be 4 tan theta, we know that our dx would be 4 secant square theta d theta, because we know that the derivative of tan theta is secant square theta. So that is why your dx will be 4 secant square theta d theta. And now if you write the integral in terms of d theta, your dx will be converted to 4 secant square theta d theta. X square will become 16 tan square theta, and this would become 16 tan square theta plus 16 in this case, right? And since we already discussed, this would be 16 times tan square theta plus 1, and tan square theta plus 1 is secant square theta, so we can write this expression as simply 4 secant square theta d theta upon 16 tan square theta 16 secant square theta in this case, right? And now if we calculate this expression, we will get 16 tan square theta times 4 secant theta in this case. And now we can cancel this 4 with this 4. Secant theta will be cancelled with 1 secant theta in the numerator. And now we will be left with calculating the integral of secant theta upon 16 tan square theta d theta in this case, right? But now, since we have our integral in terms of secant and tan theta, we know that we are most familiar with sine and cos theta expressions, right? So let's convert this expression over here in terms of sine and cos theta expressions in this case. And the way to do that is, since we know that our secant theta is 1 over cos theta, so we can write secant theta as 1 over cos theta, and then you have a 1 by 16 term as well over here. Your tan square theta term can be easily converted to sine square theta upon cos square theta, right? So cos square theta will come in the numerator, and then you have a d theta term as well. And if you cancel this cos theta with 1 cos theta in the numerator, your integral will be simplified to just calculating the integral of 1 by 16 cos theta d theta upon sine square theta in this case, right? And now you know that you can easily solve this integral using substitution. If you assume your u to be sine theta, you already have a cos theta d theta expression. So if you assume your u to be sine theta, you know that your du would be cos theta d theta. So you can easily solve this integral using substitution, right? So we'll do that. We'll assume our u to be sine theta. If we assume our u to be sine theta, we know that du is cos theta d theta. So this integral over here will be just simplified to calculating the integral of 1 by 16 times the integral of du upon u square, and then if you want to calculate this integral, it would be 1 by 16 times integral of u to the power minus 2 du, which is simply using the power rule u to the power minus 1 upon minus 1 plus the constant of integration, right? And now since your u was originally sine theta, if you want the answer to be in terms of sine theta, your answer will be 1 by 16 sine to the power minus 1 theta will become 1 by sine theta, and since you already have minus 1 in the denominator, you'll keep it as it is. So your integral expression in terms of theta will be minus 1 by 16 sine theta plus the constant of integration in this case, right? But now this answer that you got over here is in terms of theta. You know that since your original expression was in terms of dx, in terms of the variable x, you'll have to convert everything back to your original function in this case. And we'll use this conversion over here. And since we converted everything from x to theta, now since we got our answer in terms of theta, we'll have to convert our expression back from theta to the x expression over here. And the way to do that is, we already touched upon this approach in the last videos, but the basic idea is you'll use this conversion over here. So we know that our x is 4 tan theta. So if I just calculate tan theta in this case, my tan theta is x by 4. And now we'll use the basic trigonometric properties that we know. And we know that tan theta is basically perpendicular upon base, right? So if we construct a right angle triangle over here, if this is a right angle triangle and we are assuming this angle to be theta, we know that tan theta is basically perpendicular upon base. So perpendicular is x, base is 4, and now if you want to calculate this side over here using the Pythagoras theorem, you can easily calculate this side. This side would be a square plus b square, which would be x square plus 4 square, which is 16, right? And now since you want the answer to sine theta to calculate your final answer, we easily can calculate sine theta, right? We know that sine theta is basically perpendicular upon hypotenuse, right? So we know that our perpendicular is this one, the hypotenuse is this side. So perpendicular is x, hypotenuse is under root x square plus 16. So now this is the answer to your sine theta. And now if you want the final answer to your original indefinite integral in terms of x, you can easily substitute the value of sine theta in this case, right? So your answer would be simply minus 1 by 16 times x upon under root x square plus 16 plus the constant of integration. And now if you want to further simplify it, it would simply be minus under root x square plus 16 upon 16x plus the constant of integration, right? So this would be your final answer to the integral of this expression over here, right? So that's it for this video. Again, the main takeaway from this video is whenever you have an expression of the form a square plus minus b square x square, you'll most likely use trigonometric substitution in order to simplify your integral and then basically convert it to a much simpler expression than your original integral expression which was given in the question. So feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.